Math 2414, other convergence test, video 9, the ratio test. Correction from the previous video. If you were watching them, you were probably wondering why it jumped from video 7 to video 9. The answer is I can't count. Well, that's the short answer. The long answer, not that it really matters, but full disclosure, is I have a Word document, which I am now sharing with you. At least I thought it was. Here it's sharing it. Word document is. I have a Word document that I'm sharing with you where I kind of keep my videos in order. But originally this had, you're going to be glad that it didn't. Originally this had 11, 12, 13, 14, 15. See, this had about 17 videos. But I realized that I could condense some of them into a single video. And so the numbering was getting off as I was merging video topics. And I just totally forgot to merge some, and I thought it was further along the series than it was. And I was on video 8 instead of video 9. So if you were wondering why it skipped from video 7 to video 9, it's because I wasn't paying attention when I condensed the topics, and I thought we were on video 9. But now we're on video 9. And by the way, there's one more after this. Hooray for just 10. All right, so let's talk about the ratio test, which gives us another way to answer the question, are you convergent? In fact, the answer is, are you absolutely convergent? We're going to start with the series, the sum from n equals 1 to infinity of some series an. Let that be a series, and we're going to define a limit L, like we did in the limit comparison test, but a little bit differently. L is going to be the limit as n approaches infinity of the absolute value of an plus 1 over an. Let me translate what this really means. When you see something like this, you're basically saying we're going to let n be replaced with n plus 1. The best way to think about this is that this is the ratio of consecutive terms. Consecutive. Ratio of consecutive terms. Now these terms will frequently be fractions in their own right. And so we'll have what I call the next term on top and the current term on the bottom. But since the current term on the bottom is a fraction, excuse me, it'll get reciprocated. Very short on beverage here. Okay, so anyway, we set up this limit, the limit of the absolute value of the ratio of consecutive terms, and we get an answer for that limit. And based on that answer, we say one of three things. Number one, if the limit we get is less than 1, then the series converges absolutely. End of story. Which means it also converges without the absolute value, so hooray. If our limit is greater than 1, our series diverges. But if the limit is 1, then the test is inconclusive and we have to use another test. So like most convergence tests, there is an inconclusive scenario. So when should we consider using this? The answer is when you have variables in exponents, when you have variables in polynomials, when you have variables in factorials, which we haven't seen lately, we will soon. In other words, it's almost always a good time to try it. So let's try it on this one. The sum from n equals 1 to infinity of negative 3 to the nth power over n cubed. Now, if you're thinking this is an alternating series, you would be correct, because you don't have to, but you could split the negative 3 to the n as negative 1 to the n and 3 to the n to expose the alternator. Oops. To expose the alternator in the problem. But it's not necessary to do that unless you are going to just look at the part without the alternator. But regardless, let's check for the convergence using the ratio test. To do that, we have to start by setting L equal to the limit as n approaches infinity of the ratio of consecutive terms. Now, what goes in the bottom is the current term as is, so negative 3 to the nth over n cubed. What goes on top would be the next term after the nth term. In other words, you just replace all the n's with n minus 1s, and you would get negative 3, with n plus 1s. We get negative 3 to the n plus 1 over n plus 1 cubed. But if you're making a ratio of fractions, then the bottom one's always going to get flipped and multiplied. So it's bothering me not being centered. That way when I'm looking at me, I'm looking at you. If I put it over here, I have to look here to see the camera, and I'm not looking at you anymore. It bothers me. I know it's the limit things. All right, so as I was saying, we're taking the limit of the ratio of fractions, but anytime you have one fraction on top of another, you're gonna multiply by the reciprocal at the bottom. So one thing you should get acclimated to when you're setting up the ratio test is to not literally set up the ratio, because you're gonna knock it down anyway. So what I recommend doing is writing the quote unquote next term. In other words, this is where you would replace the n with an n plus 1. So negative 3 to the n plus 1 over n plus 1 cubed. Then times the reciprocal, what I call the current term. The current term is the one that you see. I currently see this, but it's going in the bottom of a fraction, so it's going to get multiplied by its reciprocal. So turn that one upside down. It is important that you get the order correct, because if you reciprocate the wrong one and your limit was less than 1, it's going to end up being greater than 1 or vice versa. Since the reciprocal of a number less than 1 is greater than 1 or vice versa, then you would draw the wrong conclusion. So it's the next term times the reciprocal of the current term. All right. Oh, I'm sorry. All this is in an absolute value. Let's get rid of the giant parentheses and replace them with gigantic absolute value. So anything that's negative becomes positive. Let's see what we get. Limit as n approaches infinity. We have, well, the negative 3's will become positive. And that's namely because of what I said a minute ago about when you have negative 3 to the nth power, you'd separate the alternator from the positive part, and the absolute value would kill the alternator. So here we can just get rid of the negative on the 3's. And so the absolute value of that would be 3 to the n plus 1. The n is positive, so we can not worry about the absolute value of n cubed. The n plus 1 cubed is positive. And then we can remove the negative on the 3 to the n as well. And at this point, we remove the absolute values. We've done the absolute values. Okay, so let's see what we can do. When you have the next power over the current power, you can just subtract the exponents. N plus 1 minus n, that's just 1. In other words, all of these cancel almost all of those, but leave a 3 behind. Where does that put us? That puts us at the limit as n approaches infinity of 3n cubed. At the bottom, we have the n plus 1 cubed. These are both third-degree polynomials. The one on the bottom is factored, but if you wanted to, you could multiply it all out. I don't need to multiply it all out. I only really need its leading term. But if you don't know n plus 1 cubed off the top of your head, I invite you to FOIL it and then multiply it out again. You should get n cubed plus 3n squared plus 3n plus 1. And if you're going like, wait, what? That's a sign that you literally need to write out all 3 parentheses, get to multiplying one pair at a time until you end up with n cubed plus 3n squared plus 3n plus 1. Oh, we're taking the limit of the ratio of polynomials and the degrees match. And when the degrees match, then it's just the ratio of the leading coefficients. Or you could use L'Hopital's rule a few times. So the limit is 3. But what does this mean? Well, since our limit is 3, that's greater than 1. Conclusion is the series diverges by the ratio test. So you set up a ratio of consecutive terms. So you multiply the next term times the reciprocal of the current, drop an absolute value on it, so any alternators are gone. Let's apply something there. Take the limit. If it's greater than 1, diverge. If it's less than 1, absolute convergence. If it's equal to 1, inconclusive. Take a look at another one. N equals 1 to infinity of 2 to the n over n factorial. Now, we haven't seen factorials lately. I briefly mentioned them in the videos about sequences, but I want to remind you what it means. A factorial is an exclamation mark, and it means to do a multiplication problem starting with that number, and then times one less than that number, and then times the next number, one less than that, until you get down to 3, 2, and 1. So we're assuming the n is an integer or a whole number, and it is because it starts at 1, and it's part of our summation. So for example, if you had 5 factorial, start with 5 and multiply all the way down to 3, all the way down to 1, equal to 120. But that's all factorial means. All right, so let's do this using the ratio test. Now, one thing you should note is that this term is already positive, so taking its absolute value changes nothing. But just to be consistent, limit as n approaches infinity of the absolute value of the next term, which would be 2 to the n plus 1, for n plus 1 factorial, times the reciprocal of the current term, so n factorial to the n. Everything in there is positive, so we can lose all that. And let's rearrange the factors so that the 2's are above each other and the factorials are above each other. Multiplication is nice and commutative like that. Now let's just take it piece by piece, or rather I should say pair by pair. What's going to happen here? Well, the exponents subtract. N plus 1 minus n is just 1. So this will reduce down to just a 2. Now the factorials may not be as obvious until you start expanding them. If we were to expand the n factorial, it would be n times n minus 1 all the way down to 3, 2, and 1. But what would the n plus 1 factorial expand to? Well, it would start with n plus 1, and then you would multiply by the next number 1 less than that. Well, n plus 1 minus 1 is just n, and 1 less than that is n minus 1. And then all the way down to 3, 2, and 1. And look at all these matching factors. The 3, 2, 1's match. In fact, everything matches. Almost. The only thing that survives is the n plus 1. Anytime you have a ratio of factorials, there's always a massive cancellation. The only thing that survives is the front end of the larger factorial, which could be more than one factor, but in this case, it was 1. So now that we've set up the limit and simplified the ratio, see what we're left with. On the top, the only thing left is 2. On the bottom, the only thing left is n plus 1. Well, that limit's easy. It's 0. The top is static. The bottom is exploding to infinity. So our limit is 0. And what does that get us? Well, if the limit's less than 1, we get absolute convergence. Kind of redundant to say absolute convergence here because it was already positive. Therefore, sticking an absolute value on it accomplishes that. Okay, so this thing is absolutely convergent, so it converges with an absolute value, but it's already positive. But regardless, so it also means it converges as is. What does it converge to? Doesn't really matter. I know it. I probably shouldn't be whispering. Later, we'll figure out that this is actually a pretty common infinite series, and it converges to e to the second power. But I'm going to get rid of that because we don't really know that now. We will later. And for those of you moving forward, what you see here is a very common series, and later on in this chapter, we'll recognize, oh, that's just the series for blah, 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 blah. All right. Oh, that was it. I just have those 2 examples. Okay, well, that's good. All right, so ratio test. All you have to do is take the limit of the absolute value of the ratio of consecutive terms and draw a conclusion based on whether that limit comes out less than 1 or greater than 1. If it comes out to be equal to 1, it's inconclusive. Oh, and by the way, and I remember why I thought there was more. I did want to show you real quick why the inconclusive thing exists, just by quickly going over these 2. The first one is a harmonic series. We already know it diverges. Second one's a P series. P is 2. We know it converges. If we did the ratio test on this, we would get L equals the limit as n approaches infinity of the ratio. We don't need the absolute value. Everything's positive. Of the next term, 1 over n plus 1, times the reciprocal of the current term. That would be the limit as n approaches infinity of n over n plus 1. But this is the limit of a ratio of polynomials and the degrees match. So the limit is the ratio of leading coefficients, 1 over 1. That limit is 1. But if we did the ratio test on the p-series, then we would do the next term, which would be 1 over n plus 1 squared, times the reciprocal of the current term. I'm not going to do all the details, but its limit is also 1. So the reason the test is inconclusive is because you can't conclude anything. On this one, the limit is 1, but we know this diverges. And on this one, the limit is also 1, but we know that it converges. Convergent p-series. So when I say the limit is 1, it's an inconclusive test. That is precisely what that means. You cannot draw a conclusion when the ratio test